So guys, 2017 higher level question 2, which is the testing. So construction of Formula 1 cars, safety, impact tests. Okay, so name and describe with the aid of a diagram a suitable impact test to examine the materials and the survival cell. Okay, so impact testing is what we're on about. Just stick that under here. So, okay, so you've got the Sharpie or the IZOD. Now they're pretty identical, and again we're going to be doing a diagram here, so I might just zoom this back a small bit. Okay, so we're going to draw a base. And kind of up from the top here, we're going to put a circle up here for our display, and then I'll just kind of slope a line around that, and just from slope that back down here. Okay, so we're gonna put I'm going to, if you had a compass, now you could use a ruler and all that, like, but we'll say if you had a compass, you know, you could do this, a very good job on this. So here is going to be our striker, okay, so this here is going to be our, I should really have used a color on this now. So that's going to be like a pendulum. Okay, so we've got a striker. Now, if it's an IZOD test, IZOD is 167 joules. So you lift it high enough for the impact to be 167 joules at impact. Now it swings down, breaks that piece, swings up to the other side. So I'm going to just put on roughly the position here. So that would be the highest point at impact, and it leaves a drag pointer. Okay, so the drag pointer there is just an arrow that it leaves at the highest point. Now down here we're going to have a voice, something like this, and our test piece, which is going to have a notch in it. And I'll colour that in now in a different colour here. Okay, so here is, so I'm going to decide that we're going to go with the IZOD, right? So we describe the IZOD. You could have the Sharpie or the IZOD, but I'm going to say that this is the IZOD. Okay, so the striking pendulum is raised for 167 joules of impact. The test piece is a notched bar it is held at the bottom / only at one end. The notch faces the striker. Okay, so the notch is facing the striker. Okay, and the striker breaks the piece and swings up past. The drag pointer is left at the highest point, giving the result. Okay, so that's the basis of how it works, and I might just colour in the voice here in red. So the red thing is the voice. And the drag pointer, I'll just label that, that's the drag pointer. And I'll put some readings on this as well, just like a clock there, just a few measurements. So, that's the basis of how it works. Now, we were asked there to describe with a diagram the test. And said outline with sketches the expected results of the test on a brittle material and a tough material. Okay, so I'm going to use the one sketch for all of it, I think. Okay, so I mean, I could go drawing the whole thing again, but like, is it worth the bother? Okay, so it's going to break the test piece, so we could draw down here that the test piece is going to be broken. So I'll just draw a broken test piece. So that would be the V. And this would be the rest of it there then. Okay. So the test piece snaps in a brittle material. So like in a brittle material it would be knocked off and rolling around the floor probably. So a test piece snaps in a brittle material, and in a tough material it could bend a lot before breaking, slowing down the striking pendulum, so it won't, I'll just say, go as high. And if you wanted to, I don't think it's probably an overkill to go drawing this here now, but like you could kind of draw this here now, something like this. You know, here's our V. So like, you know, that would be if it was very, very ductile or whatever there, and it might, you know, it bent way, way back, and, you know, mightn't have even broke. Or it would bend away back before it breaks. But either way, so I'm going to say, to go back up here to our diagram, like that would be a brittle. And I'm going to put in another one down lower and say that this is a tough material. So I'm going to put a color in here as well, just to make sure that they can notice these. So there's our striker. So a tough material will slow it down a lot. So tough. It's like a tough cornerback will slow down the forward a lot, whereas a brittle cornerback won't stop him too much at all. So so I'm going to say there, just see the diagram in pink. So I'm just saying to see that done above in the diagram there in pink, and just make sure if you do something like that, that you make sure whoever is checking it will notice it. Okay, so that is A. Now, immediately, first thing I always look for doing these is it stress strain or load extension? And this is load extension, which is kind of the first set of measurements you get. You could convert it, because if I divided these by the cross-sectional area, I'd change it into stress. And if I divided this by the original gauge length, which is the two dots on the test piece, this would become strain. So I could change this to stress strain if I knew the cross-sectional area and the gauge length, which I do. But just to know that this is kind of the first and simplest set of numbers for one of these. So anyway, it said there, blah, 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 12 millimeter diameter, 80 gauge length. Plot the diagram and indicate elastic limit, necking, fracture. So I'm going to do that first. So again, just check there, what is the highest load which is going to be going vertical and extension? So it's 8 and 180. So so I would do the 180 first on the vertical axis here. So 180. So even if you took 10 lines, 2, 4, 6, 8, 10, like that'll probably do, yeah. And I want 8 in this direction, so I'm gonna go with 20s, 4. Okay, so 0, 1, 2. Okay, so that's our extension in millimeters, and this is our load in kilonewtons. Alright, so I wanted this up to 200, so so 20, 40, 60, 80, 100. Okay, so 20, 40, 60, 80, 100, 120, 40, 160, 180, 200. So that'll do. And okay, so the first one we had in there was when the load was 30 at an extension of 0.2. Okay, now I will measure this, I think. All right, so that is 2, that would be 1. So sorry, that's 1, so 0.2 would be 4 mil. Okay, so that would be 0.2. And the next one I have is 0.5, which would be here in the middle, and 0.8. So there's a lot going on in the start. And then it goes 0.9 as well. God almighty. So You can see there that it would be handier to have the old graph paper, alright. So I'll just draw a few vertical lines for these before I go any further. So 0.2, 0.5, 0.8, 0.9. And 1.5 then. Okay, so then there's 1.5 and 2. So 1.5 would be here, and 2, 2.5, 3. So I need 2.5, 3, 5.6. Okay, so 5.6. And 8. All right. So I'll just put my vertical lines on for those last couple there. So I need 1.5, 2, 2.5, 3, 5.6, and 8. Okay, so the 0.2 has a load of 30, 0.5 is a load of 80, 0.8 is a load of 126, 120, that would be 130, so about here. 0.9 is 146, 140, 150, so about here. 1.5 is 153, 2 is 147, 2.5 is 152, 152, 3 is 162, 5.6, 181, and 8 is 174. 160, 174, so there. Okay, so let's draw that there now. Now always check in the start if there's a elastic region which is a straight line. So how far does that go? And like there's a lot of this is the elastic region, and then we've got after that so there's our curve. So I want to label this, so I'll just put this in blue here, is the elastic region. Here's the yield, where that's where in the elastic region, if you took away the extension, if you release the force on it, it'll go back to its normal size again. But once it goes beyond the yield, you've ruptured it. Then it's like pulling your arm out of your socket. It's not going back. Like you've done permanent damage then, and that's the end of the elastic region. It's stuck now. It's strained. So this is the next section of this here. Then is our duct. I'll just color this in here. This is our plastic or ductile. That's our plastic extension. All the ways. Now this is the ultimate tensile strength point here. That's the maximum load that it took during the whole thing, which was 181 from the test. So I'm just going to stick that in there. That's 181 kilonewtons there. That was the highest force that it took. And this is our ductile extension here. So the cup and cone would be forming here now along this. Okay, so it said outline with sketch. No, it said name and describe. And then, sorry, no, yeah. On part 2 it said indicate the following points on your graph. So the elastic limit would be okay, so I wanted that, so I'm going to just make sure now that whoever's correcting it knows that that's a key point there. So that's our elastic limit. The start of necking and the fracture point. And again there I'm going to just highlight the start of necking and fracture point. Okay, so that's the elastic limit, end of the straight line. Start of necking is after the maximum force there, so the bar starts to stretch and get thinner than like pulling out chewing gum or whatever. So that's all of them, and the ultimate tensile strength. Okay, now here is the problem, minor problem, but the ultimate tensile strength comes from here, and I said it was 181, but the ultimate is the maximum force over the cross-sectional area, CSA, sorry. So cross-sectional area, so our maximum force divided by our cross-sectional area. So we know the maximum force is 181 divided by, now the cross-sectional area, I'm going to take you back here, and they told you that this was 12 millimeter diameter. So this goes back to maths, and I'm going to just go back here for a second. So your 12 millimeter diameter here. So that's a diameter 12 millimeter bar. So you want the cross-sectional area of that circle, which is going to be pi times the diameter. So that's going to be 3.14 multiplied by diameter 12 is equal to, just check that out there in the calculator 1 sec. Okay, so as I was saying there, right, so the area of this is pi r squared. So the circumference is pi times the diameter. So the area of this is pi r squared. So the radius is 6 squared. So it's 3.14 by 36 is equal to 113. So our cross-sectional area is 113, and that means our ultimate tensile strength is 181 divided by 113, which works out is equal to 1.6. Oh, sorry guys, my battery just died there, so I finished off that there. I didn't even notice, but so look, the ultimate tensile strength is the maximum force over the cross-sectional area. Now, in this there, they told us that it was diameter 12. So, diameter 12 is radius 6. So the area of the circle is, and again, what circle? The area of the circle, I'm presuming, I suppose, that we know that where this is coming from. But basically where it ruptures. So, where your dumbbell styled test piece breaks here. Okay, so the area of that circle, it's radius 6. So diameter 12, radius 6. So it's pi times r squared. So it's 3.414 times 36 is 113. So it's the maximum force, which is 113, divided by or 181 should I say. Maximum force 181 divided by the cross-sectional area of this, which is 113. So that's millimeters squared. That's kilonewtons. So 1.6 kilonewtons per millimeter squared. And the last part of this there, I didn't realize I wasn't recording. So the X-ray test there, describe the test. So you've got an emitter. In this case, I just put in a weld. Now that's a good one to use actually, because it's quick to draw. So just put in a weld and put in your X-rays. There's the collector here, and let's just say, and that's giving a digital readout there now as opposed to a chart. So basically you just have to show the collector connected up to a monitor. So the emitter shoots the X-rays through the test piece, and it'll show up any flaws, or if there's a solid piece, to be internal defects on the monitor. And the safety issues there, 2 safety hazards is causes cancer, can cause damage to your eyes, so you need to wear proper eye protection, protective clothing, make sure other people are restricted, use it for the least time possible and the lowest setting that will do the job. Okay, so keep the power, you know, as the lowest you can get away with while still doing it properly. So that's the end of that there. So I hope that all this came out. I'll check there later.